Hello everyone, I'm Hiroaki Igarashi from Denso Corporation, Japan. Today, I would like to introduce multitask curriculum learning based on gradient similarity. First, background. For robotics application like autonomous driving, several perceptual tasks are required. For example, object detection and semantic segmentation. If we have each model for each task, then it will be computationally complex. Multitask learning could be one approach to reduce the complexity. As shown in this figure, MTL shares a portion of the network between multiple tasks and can reduce the complexity. However, there are several challenges in MTL. Gradient conflict is one of them. In MTL, loss functions are defined for each task, and gradients are backplopped for each task as well. Therefore, in shared DNN, each task may update parameter into different direction. This is called gradient conflict. Since each task may have adverse effects on the other, gradient conflict may lead to insufficient model performance. There are several approaches to tackle with gradient conflicts. PC-grad is one of them. As shown in this figure, by clipping orthogonal components for the other task, PC-grad removes conflicting components of each gradient. However, PC-grad may not work well in some cases. This figure shows the case that each task has a big difference in magnitude of gradients. Left-hand side shows the case without PC-grad, and right-hand side shows the case with PC-grad, and acquired gradients are represented in purple arrows. You can see that the acquired gradient by PC-grad is much different from the original one. Therefore, we can say that a converged solution by PC-grad is no longer optimal for original objective due to gradient manipulation. Next, I will introduce proposed method. Proposed method is named multitask curriculum learning based on gradient similarity. MCLGS introduces a curriculum learning strategy based on gradient similarity in MTL. Curriculum learning is a training paradigm that orders training samples from easy to hard, like a human learning strategy. It is well known that these strategies improve model performance. To introduce MTL-specific curriculum, we need to define difficulty of samples in MTL. Here, we use amount of gradient conflicts for the difficulty. This figure shows an overview of MCLGS. X-coordinate represents amount of gradient conflicts, and Y-coordinate shows training step T. As shown in upper side, gradients are weighted if they are more similar in the early stage of training. As shown in lower side, gradients are not weighted at all at the end of training. While PC-grad manipulates gradients, MCLGS just downweights samples that generate gradient conflict in the early stage of training. This slide shows a formulation of MCLGS. To realize such a curriculum, we introduce a simple weighting function, and it consists of scaling function and a pacing function. The scaling function is a cosine similarity of two gradients, and the pacing function is a decreasing function of training time such that the output of weighting function will be 1 for a large T. By using this weighting function, proposed update rule is shown like this. This slide shows how MCLGS works during training. MCLGS is applied on the BDD100K dataset, which contains two tasks of semantic segmentation and object detection. Left-hand side shows training step T versus cosine similarity, As shown in the figure, the cosine similarity is decreasing during training, and the right-hand side shows training step t versus output of weighting function. As shown in the figure, corresponding to the cosine similarity, the weight is also decreasing. And as learning progresses, the variance of weight is gradually decreasing, and finally weight converges to a fixed value of 1. This is because the pacing function works how the samples are gradually included as training progresses. Next slide is experimental results. First result is on the NYU V2 dataset, which contains 3 tasks of semantic segmentation, depth estimation, and surface normal prediction. As shown in the table, MCLGS achieved 2.21% of task average improvement from STL baseline, and it outperforms all baseline including MGDA, PC-GLAD, GLAD drop, and CA-GLAD. Additionally, combination of MCLGS and CA-GLAD achieved the best result of 3.37% improvement. Second result is on the BDD100K dataset. You can see that all conventional methods doesn't work well on this dataset compared with MTL baseline. However, MCLGS still achieved better performance of 4.03% of task average improvement from STL baseline. Let's conclude our presentation with a summary. In this presentation, we proposed MCLGS to avoid gradient conflict, which is one of the major challenges in MTL. While conventional methods manipulate gradients to remove the conflicts, MCLGS introduced a curriculum learning strategy, and it just downweights samples which generate the conflict in the early stage of training. Therefore, MCLGS retains the original objectives toward the end of training. We experimentally confirmed that the MCLGS outperforms all baseline including MGDA, PC-GLAD, GLAD drop, and PC-GLAD on the NYU V2 dataset and the BDD100K dataset as well. Thank you.